Aditya Patankar, and I'm part of the Interacting Robotic Systems Laboratory at Stony Brook University, New York. Today, I will be talking about computing task-dependent grasp metric using second-order cone programs. Grasp quality measures or grasp metrics are a key component of many grasp planning algorithms. Generally, a multitude of grasps can be used to hold an object effectively. As shown in the figure on the left, a common purpose of holding an object is to pick and place the object at a certain pose. Another common purpose of holding an object is to perform a specified task. The figure on the right shows two such examples. In order to perform tasks such as opening a drawer or turning a doorknob, the grasp has to generate enough force or moment along a particular axis as shown in the figure. In such scenarios, a grasp metric or quality measure should reflect the purpose of holding the object. Common tasks such as opening a door or a drawer can be represented as a single constant screw motion about a particular axis. The main advantage of this representation is that it satisfies the kinematic motion constraint associated with a particular task. For example, while opening a door, the revolute joint constraint at the door hinge should be satisfied. Another example is of pivoting objects with the help of environment. We need to satisfy the constraint at the object environment contact that the object does not penetrate the ground as seen in the animation on the right. This constraint can be readily satisfied if the pivoting motion is represented as a constant screw motion about the pivoting edge. Therefore, our overall goal in this paper is to formalize the notion of a task using screw motions and to develop grasp metric to evaluate different grasps used for executing tasks corresponding to such motions. Please note that in our paper, we consider a grasp to be a set of contact locations unless stated otherwise. Our key contribution in this paper is that we have defined a task as a unit screw corresponding to a constant screw motion or wrench, about which the fingers or manipulators need to apply an equivalent wrench to generate the desired motion. We have defined a task-dependent grasp metric as the maximum magnitude of wrench that can be applied along the task screw. We have formulated the problem of computing the metric as a second-order cone program while considering the contact constraints, equilibrium constraints, manipulator joint torque constraints. Our formulation also allows for different upper limits on the magnitude of contact forces at different locations. Since the SOCP is a convex optimization problem, it can be solved efficiently with existing optimization methods like interior point methods. Recall that any rigid body motion can be expressed as a screw motion, which is defined by a rotation about an axis along with a translation along the same axis. Consider the motion of a rigid body from one pose C1 to another pose C2. This motion can be conveniently expressed as screw motion about the axis S. The axis S is known as the screw axis and is characterized by the unit vector L and a point Q on the axis. Constant screw motion is the motion where only the magnitude of the screw associated with the twist changes and not the pitch and the axis. Similarly, a constant screw wrench is a wrench where only the magnitude of the screw associated with the wrench changes. A second-order cone program is a special class of convex optimization problems, and they are defined as follows. We have a linear objective function subject to a second-order cone constraint. Here, x is the optimization variable, and a and f are matrices of appropriate dimensions. As we will show later, our optimization formulation for computing the grasp metric will have the mathematical structure of a SOCP. There is a significant amount of literature on computing task-dependent and task-independent metrics. Here, we will focus more on the task-dependent metrics. Different formulations, including linear programming and linear matrix inequalities, have been used for grasp analysis using metrics. These methods differ in the way the friction cone is approximated. Linear programming approaches assume that the friction cone is a polyhedron, whereas linear matrix inequalities and SOCPs both use quadratic friction cone models. Hashke et al. Have defined a task as a unit wrench in the task wrench space, which is similar to our definition. However, they have formulated the problem of computing the grasp metric using LMIs. In context of grasp analysis, it has been demonstrated by Boyd et al. That the SOCP formulation leads to faster algorithms and efficient solutions. In all the papers above, only the contact forces corresponding to the object manipulator contacts are considered. In this paper, we will consider object environment contacts along where there is no direct control of interaction forces, along with joint torque constraints and external wrenches. This is our general optimization problem formulation for computing the task-dependent grasp metric. The objective function is subjected to the following constraints: the equilibrium constraint, the contact constraints, followed by the manipulator joint torque constraints. I will explain all these constraints one by one in the upcoming slides. Contact constraints. First, we have the contact constraints. The contact constraints are the constraints imposed by the contact model on the forces that arise at the contact locations. In general, we have two contact models: point contact with friction model and the soft finger contact with elliptic approximation. In our paper, we have assumed that the contacts between the object and the environment are point contacts with friction, and the contacts between the object and the manipulator are soft finger contacts. Note that both the friction cones for the point contact with friction model and the soft finger contact model are second order cone constraints. To guarantee that the object is not damaged by the contact forces at the contacts between the object and the manipulator tips, we can consider an upper bound constraint on the normal contact forces. Here, Fn max is the upper limit on the normal contact forces. It is important to remember that this upper limit can be different for different locations. Both the second order cone constraints for the friction models can be expressed compactly as shown here at the bottom of the slide. While performing any manipulation or grasping task with the help of robotic manipulators, we need to compute the joint torques which generate the necessary wrenches at the object manipulator contacts. The relationship between the joint torques and the contact wrenches is given by this equation. Here, Ji is the Jacobian matrix of the ith manipulator and tau g is the torque for balancing the gravitational forces on a manipulator. The above equation can be expressed more compactly as follows. To ensure that the joint actuators are able to generate the required joint torques, we need to specify the joint constraints as given. In this equation, tau min and tau max are the lower and upper limits of the manipulator joint torques respectively. These constraints are also a set of linear equations. The concept of grasp wrench space has been used extensively to quantify grasps. In our paper, we provide a more general definition of the grasp wrench space. It is a set of all possible wrenches that a grasp, including the manipulators, environment, and external wrenches, can apply to an object while satisfying all the related constraints. Mathematically, this set can be expressed as follows, where FC is the set of all object manipulator contact wrenches, FE is the set of all object environment contact wrenches. Both FC and FE have to satisfy the friction cone constraints at the contacts. F external is the total external wrench acting on the object. GC is the grasp matrix, and GE is the environment contact matrix. Note that the grasp wrench space defined above is a convex set and includes the origin 0. It is important to note that our definition of the grasp wrench space is different from any existing definitions, as we do not assume the contact forces to have the same upper limit normalized to the same value, because in practice, the force limit at all the contacts may not be the same. Moreover, environmental contacts and external forces may also be present and need to be considered while evaluating the grasp. Our definition of the grasp wrench space allows us to take into consideration these additional wrenches as they may also assist in performing the task. One clear example is the use of object environment contacts to manipulate heavy objects as shown in the figure. When we do this, the forces at the object environment contact can be used to partly balance the weight of the object. In this slide, we will be formalizing our definition of a task and our task-dependent grasp metric. According to Poinset's theorem, every wrench applied to a rigid body is equivalent to a force applied along a screw axis and a torque about the same axis. In our formulation, we have defined a task as a constant screw motion or a wrench along a given axis. Thus, we are interested in finding a wrench omega task among all the possible wrenches that a grasp can generate equivalent to a wrench along the screw axis. This definition can be intuitively used to characterize tasks such as opening and closing a door or operating a screwdriver. For example, in order to efficiently operate a screwdriver, the user needs to generate a constant screw wrench along the screw axis. Recall that the screw axis S can be defined by using a unit vector L along the axis and a point Q on the axis. Using this definition, our task wrench, omega task, can be represented by a force Fs along the screw axis and a torque, tau s, about the axis S. Here, H is known as the screw pitch. When the omega task has only pure torque about the screw axis, the screw pitch is equal to infinity. It is a real valued number otherwise. Therefore, we can represent any spatial task wrench omega task using 3 screw coordinates, the magnitude Fs or tau s, the pitch H, and the axis S represented by L and Q. Thus, by representing the task as a constant screw motion or wrench along a given axis S with a given pitch and magnitude, we define a task-dependent grasp metric eta as the maximum magnitude of a wrench that a grasp can generate along a given screw axis S. As described in our previous slide, we are interested in computing the maximum amount of wrench that a grasp can generate along a given screw axis S. This serves as the linear objective function of our general optimization formulation. The friction cone constraints are second-order cone constraints, and all the other constraints are linear. Thus, our optimization problem for computing the task-dependent grasp metric can be modeled as a SOCP. In this paper, we have assumed that the manipulation is quasi-static, and therefore the inertia effects and dynamic forces are very small and can be ignored. The grasp metric computed using our SOCP-based formulation presented here is for a particular instant. However, we can use this formulation to compute a grasp metric during the whole task. This is because we can define a complex task as a sequence of constant screw motions about different screw axes. We have evaluated our proposed metric for two scenarios. In both cases, we want to generate a constant screw motion along a given axis S by applying a wrench along the same axis. For simplicity purposes, we have not considered the manipulator joint torque constraints in our formulation. In both cases, our objective is to evaluate different contact locations based on the value of our task-dependent metric. In the first example, we evaluate our grasp metric eta while turning a door handle about the screw axis S by a pair of antipodal contact locations. The task-dependent grasp metric here is the magnitude of the maximum moment that the grasp can generate about the screw axis. Since we are interested in only the moment of the screw axis, the screw pitch is infinity. The torque of the torsion spring is given by kt theta, where kt is the spring constant. Since the torsion spring generates a moment about the z-axis of the environment contact E, its effect needs to be considered in the wrench applied at the same location. There is also a restriction on the maximum grip force which can be applied at the antipodal contact locations. The simulation parameters have been described in the table at the bottom. Figure 9 on the left shows the variation of the value of the grasp metric eta along the y-axis and the angle of rotation of the door angle theta on the x-axis for 4 different positions of the antipodal contact locations. From the results, it is evident that as we increase the value of xe, that is move along the x-axis, the grasp is able to generate a larger movement along the axis s to turn the door handle. In our second example, we evaluate a metric for a dual-handed quasi-static manipulation of a cuboid-shaped object with the help of environment contact. We consider two different tasks. The first task is pivoting the object about a screw axis S1, which passes through the edge in contact with the environment, as shown in the figure. For this task, we consider the screw pitch H is infinity. The grasp metric in this task is the maximum moment that the grasp can provide about the screw axis in both the clockwise and counterclockwise directions. Second task is sliding the object along the screw axis S2, which passes through the object center of mass. In this task, we first pivot the object at a particular angle alpha and then slide it along the screw axis S2. The screw pitch for this task is 0, and thus the grasp metric in this task is the magnitude of maximum force that the grasp can generate along the screw axis in both the positive and negative x directions. For both these tasks, we consider two object end effector contact reference frames and two object environment contact reference frames. Also, for both tasks, the external wrench acting with the environment contact is expressed as follows. In this slide, we'll discuss the results of the pivoting task. Figure 11 on the left demonstrates the variation of the value of the grasp eta for different rotation angle of the object alpha with respect to the supporting surface for both clockwise and counterclockwise directions. We studied this for three different positions of the end effector along the x-axis from the centroid. From the results, it is evident that the value of the metric changes due to the effect of the object weight during the pivoting motion. Moreover, increasing the distance between the object manipulator contacts and the axis S1, the grasp is able to resist larger disturbance torque along the screw axis in both the clockwise and counterclockwise directions. Another important observation is that as we increase the angle alpha from the support surface, the maximum disturbance torque that the grasp can resist along the axis S1 in the counterclockwise direction increases, whereas the disturbance torque in the clockwise direction decreases. This is solely due to the effect of the object weight and its variation due to the change in the rotation angle alpha. In the figure 12, the grasp metric eta2 along the y-axis with respect is in figure 12, the grasp metric is represented along the y-axis with respect to the angle alpha along the x-axis for two different positions of the end effector as shown. From the results, we can see that for a particular grasp with alpha is equals to 50 degrees and xe is equals to 0.4 L, the maximum disturbance force exerted at the object center of mass that the grasp can resist in the positive x direction is larger than the force that the grasp can resist in the negative x direction. This is because the disturbance forces for pushing the object in the negative x direction result in lower normal forces at the environment contacts as compared to the positive x direction. In this paper, we have defined a task as a constant screw motion or wrench that needs to be applied along the screw axis in order to perform the specific task. We have presented a second-order cone program for computing a task-dependent grasp metric while considering the different physical constraints and incorporating separate bounds in the magnitude of contact forces at different object manipulator contacts. Given the screw axis for a particular task, the object pose and different object contact locations, our metric can be used to evaluate and compare different object manipulator contact locations. In future work, we plan on addressing one of the key limitations of our metric, that is its robustness to unknown disturbances. We also plan on integrating our metric with existing grasp planning algorithms for manipulation tasks, especially the ones where the object is in contact with the environment, for example, pivoting an object about a corner.